looking at each of the truth tables, the most important thing for you to consider is understanding which part of the truth table is just all of your different options, and which part of the truth table are you making a decision about. So we talked about, and I had a little red line, this part of the truth table here is where you're just laying out all of your options for the different combinations of things that could be happening. And if it's easier, I noticed on the quiz some of you had a better time with the truth table when you gave yourself a story. So if your story is, let P equal I will do homework, let Q equal I will practice. So then you can think about all the different combinations of things that can happen. I can do my homework and I can practice. I can do my homework and not practice. I cannot do my homework but still practice. So what we're doing in these first two columns, when you have these blanks, I need you to make sure that you understand this is not a decision-making moment for you. That's you just putting down all the different combinations of possibilities of things that could happen. Nod your heads if that makes sense to you. So you all have a red color pencil, and if it makes it easier for you to draw that box around the P's and Q's, then that can have you making sure that you're thinking about, this is not an opportunity for me to say, oh, this is true and this is true. This is just you recognizing, here's all the different things that could happen. All right. Our next conversation has to have you looking at and paying attention to what is happening. And this is a super review on the difference between a conditional statement, that's an if-then, and that's that arrow. If this happens, then this will happen. That's a conditional statement. So where you see those arrows, now this is a special biconditional, meaning that it is true in all directions, right? If P then Q and P then Q, or Q then P is also true. Versus, and here's another conditional, versus a compound statement. So we talked about the difference between conditional and compound. A compound statement is going to be where you have and or. That's our conjunction and our disjunction. And that's just a combination of two statements together. And whether or not they both need to be true, like the inside of this, or whether either one needs to be true, like that whole diagram. So when you're thinking about the Venn diagrams, the difference between a conditional and a compound statement, if you're a visual learner, maybe that picture might make it easier. All right, time for me to stop talking. Time for you and your partner to talk through these about what it takes for them to be true and not true. Would you please turn to your partner and say, let's go. All right, so let's come back and look at some of these, because I want you to have in your head what each of these statements are and what ends up happening with what they tell us. Okay, if it's an and statement, so this is a compound statement because, and then it's a conjunction. And the conjunction we know of as the and. And with the and, both statements have to be true for it to be true. So that's why this is a false and everything's false. This is the most specific of statements. In order for both things to be true, they have to be true. So if you want to think about making your mom super happy, you will do your homework and go to practice. Let's say she says, look, you're a student athlete. Both. You have to do your homework and you will go to practice. So the only way you're in good standing is if you do them both. Does that make sense to you? Okay. So now we come down here, and you've got some leadway with this mom. This mom says, look, just as long as you get one of those two things done, I'm okay with that. So this is, again, a compound statement because it's two ideas together, but instead of being a conjunction, who remembers what this one's called? Yeah, this is my disjunction. And we know of it as our or statement, recognizing as long as one of those two things is true, then I'm in good standing. So here's a true, here's a true, this is a true, this is a false. The only way you're going to be in big trouble is if you don't do your homework or go to practice. You okay with that? So when we start playing around with these with this statement down here, it might be easier. I was telling Olivia and Sarah, it might be easier if you need to know what not P is equal to. It might be easier if you make another column of what not P is, because that's going to negate the truth value of that P. So when I'm filling in all my possibilities, that's why this one has to be true, because it's, again, a compound statement, and it's a conjunction with this negation in it. So I'm still looking for the only time it's true is when both conditions happen. So we're going to look at this being a false and a false and a false. Everyone okay with that?
It says for the third column, what I put was, it says tweet. Oh, never mind.
Are we good? Yeah. Fantastic. Way to solve your own problems. Answer your own questions, Lily. Go ahead. So, number 3, because what I'm looking at is not P and Q. I first have to give myself what not P is. So once I look at all those possibilities of not P, false, false, true, true, since it's an and statement, they both have to be true in order for me to have a truth value of true. So instead of looking at P, I'm looking at not P. Does that make sense now?
Yeah.
Okay. Here's the one that gets everybody because it's the conditional. So if I talk about a conditional statement, I'm talking about an if-then situation. And I'm bound by that if-then conversations. So when I go ahead and I enter in everything that's possible, when I talk about those green trues and falses are just filling out my chart of what could happen. All right. So when you look at, and I want to make sure you can understand, your math space, I think, does a pretty good job of explaining this one. So I'm going to pull it up because I know this is a struggle. You have the ability to go to math space as a textbook and look things up. And I'm worried that you don't all know that. So when you go to math space, you look for this icon. That's where the book is. It should be on Fairfax Geometry Honors. You can also change your textbook to the 2020 edition. It says a few things a little bit different. I prefer the honors version. When you look at each of this is all the stuff that we're going to learn. So think about each of the chapters in a textbook, right? So as you click on where we are, logic and reasoning, we can go ahead and look at the truth tables, and they give you an options of practice questions, and then you can look at the actual lesson that goes with this. So for those of you who feel like you need more practice, you can do this on your own. You can explore math space on your own. You don't need me to assign it to you. Think about a textbook that you go back and look at more help. Here is the truth table for your conditional. If P then Q are both true, then that's a true statement. P happens, Q happens, I'm good to go. If P then Q is a true statement, P happens but Q doesn't, then the statement's false. If neither one happens, the statement's true. But this one here is the one that jacks kids up. So I want to make sure you understand why that is true. So let's go ahead and look at it together. The only way if P then Q is false is when the antecedent is true but the consequential is false. So the only way that it comes out false is if this output is false, but this is true. Okay, we need to explore why the truth table is like this row by row. 3 of the 4 possibilities make sense, but there is one row, row 3, that seems to be counterintuitive. Row 1, straightforward, not a problem. Row 2, reasonable, not a problem. And they give you an example of, if we eat an apple, then you'll feel better. Okay, I ate the apple, I don't feel better. 4 is a little trickier. I don't eat the apple, I don't feel better, so I can assume that whole, the doctor says, eat an apple a day to keep the doctor away, that's going to be true. If you don't eat the apple, but you still end up feeling better, then what the doctor said is deemed true. The reason that even though you feel better, you didn't prove that the doctor was wrong in his advice. At the end of the day, you ended up feeling better. It's an interesting conversation when it comes to, because my outcome was true, we're going to call that conditional true. And that's the one that sometimes gets kids a little bit messed up. But here we go. True, true. Okay, this one's false. This one's true. And this one is true. Because it's not a compound statement, it's a conditional that's if-then related. Sound okay? Christian, does that answer your question? All right, let's take a look at 5. If Q, then P. Now, what you need to understand is with this example, I'm talking about this one first. So take a look back at your other table where you have if P, then Q. And now I want you to think about Q first in the same context that you rationalized number 4. Talk to your partner and agree on, like there was money on it. Agree what your outcome should say, true, false. Turn it top, go.
Oh, yeah.
Thumbs up if you got it. Yeah. Because it's if Q then P, this one's true because of that outcome being true. Are you with me there? The interesting thing is, hey friends, this is our converse. If we have our if-then statement down here, we can call this our converse. Just taking a look at this one, what are you going to call this one? What kind of statement is it? Yep. Here's our inverse. And if it's easier for you to think of not P and not Q, because you're looking at the opposites in each story. So when I'm talking about not P and not Q, it's easier if I make that extra column and I can say false, false. What is that going to be? False, true. What is that going to be? Because that output, when that output is true, then we can say that that ended up being a true story. The only time that it is proven false, for sure, is if I have that output of Q false when my P was true, or my not P was true. All right, if this is the converse and this is the inverse, what is this, good friend? They're contrapositive. And the contrapositive of my statement, again, if it's easier for you to compare not P and not Q, give yourself a false, false, true, true for not P, and a false, true, true for not Q. If they're both false, if my true gives me a false outcome, my false gives me a true outcome, and then the truths. All right, so now we got to go with our biconditional. So here is our biconditional. Statement. And in order for it to be biconditional, the inverse and converse have to both be true, right? Which means that we're looking at a true, false, false, true scenario. Thumbs up if you and your partner got that. Go ahead.
I just thought it was interesting. If you're looking at the charts, if they're all laid out the same way, the conditional and the contrapositive, they have the same pattern, and the converse and the inverse have the same.
Okay, so that's a great observation. Take a look at what Maggie's saying. Because we know our statements that are linked in truth, our converse and inverse are linked in truth value, and so is our implication and our contrapositive, they end up having the same pattern of true falses, true falses. So smart enough. That's a great observation. All right, let's take a look at the back. Here we go in the back. So this is similar to the truth table that was on your quiz. The difference between your negation being on the outside is you and your partner are going to figure this out first and then negate it. What's interesting is that's already figured out for you. This negation that's here is just going to be P or not Q, so it might be beneficial for you to make a list of what not Q looks like. After you and your partner fill out the truth table, go ahead and have a good time with these conditional statements. And then check out what happens once I get 3 statements built in. And you can have a good time with that. All right, turn to your partner and say, let's go.
All right.
All right, check out my table with yours. Anything you want to talk about? All right, as far as these statements here for number 2, I will go to the football game and I will paint my face red and black. I will go to the football game or I will not sit with my parents. For C, make sure you know that the conversation starts here, where you have, I will not sit with my parents, and I will paint my face red and black, or I will go to the football game. Here, our conversation starts here, where I will sit with my parents, and I will paint my face red and black, or I will go to the football game. Yes. Sure. Go ahead. Because the order of operations pulls you into the parentheses first. Okay? That's a great question. Are we good for us? Okay. All right. So when we come down here, we're not going to be too worried about this. This is more of an extension activity for you for anything else. The most important thing is that you take care in filling out your table in a pattern so that all of your possibilities are obvious. And I have found it easier to fill out my table using this pattern because it guarantees that I hit every single possibility from all statements being true to all statements being false. The really cool thing about this table is that it's set up to get me to this column, and it's smart about how it goes through our conversations. So not Q, okay, so this would be false, false, true, true, false, false, true, true. So now when I want to talk about P and not Q, I'm going to be looking at P and I'm going to be looking at not Q. Anytime I have both statements matching, it's going to be true because I know that this is a conjunction. And in conjunction, both statements have to be true. So I've got a false, a true, a true, a false, a false, a false, a false. Everybody okay with that? Now, if you look at that, if you notice that this statement here exactly matches this one, so I'm ready for when I need that. All I'm going to have to do is look at that column. But before I get there, I need to look at P and R. So in order to look at P and R, the columns that I'm caring about are, here's P, that matters, and here's R. I'm going to look at that. It's a disjunction, so in order for there to be a true, all I need is for one of the things to be true. So I'm good here, I'm good here, I'm good here, I'm good here, good, false, good, false. Now the interesting thing is, because I'm all set up, all I need to do is look at these, oops, you knew I couldn't do it twice. See if I can get it. I want to get just that. Is it going to let me take it? There we go. Those are the only two columns that I need to look at. So taking something that initially seems completely overwhelming, and I break it down bit by bit. Now all I need to do is look at those two columns to figure out, because it's an or statement, all I need is one true in order for it to be true. So what the truth table does is it helps me organize all my possibilities. And if I'm looking at the validity of something happening, it makes it easy for me to see all the possibilities. So for the friends that asked for a truth table, does this help? Okay. All right. Here's what I want to do, I want to take some time to go back and talk from the very beginning of the unit and make sure that we've kind of reviewed so that you understand what it is. So would you please do the great paper shuffle right now and take out all your Unit 2 notes. Yep, all of your Unit 2 notes. So I'm going to tell you the story of Unit 2 from day 1. Like I'm reading a little storybook. On the first day of Unit 2, we talked about patterns. And then we talked about the homework that you did from the very start. If you are a friend that has a 3-ring binder, the telling of this story naturally makes sense because you turn the pages just like you do a storybook. If you're not organized yet, why not? How can we convince you that getting a binder, putting your papers in order, makes a difference? If you're right now sorting through and you're finding English and Spanish and science and social studies, you are wasting your study time by sorting through things that do nothing but cloud your geometry brain. All right, why did we do this lesson? For this lesson, we were all about finding patterns and using inductive reasoning so that we could complete the pattern. And that's what we talked about on our first lesson day in 2-1. Now, if you haven't picked up on our organization system, let me be the first to tell you that up here in the top corner is which lesson of which unit. So the first lesson of Unit 2, we had 2 sets of notes. In lesson A, we talked about inductive reasoning. We talked about having a conjecture or a proposition of what you think is going to happen, and waiting until somebody provides you with a counterexample that proves you right or wrong. After that lesson, we talked about putting those statements in a more formalized language. Let's go ahead and have an if, P, then Q. Let's go ahead and make our statements in an if-then form, because then we can test to see if it works by saying it forwards and backwards and negating each of the different statements. And when we did this, we learned that the converse and inverse were not always true, but they were linked together as a truth statement. That's when we had our first conversations about our conditionals, our baseball players and our athletes, and here for this one we talked about our colors. If it's blue, then it's a color, but not all colors are blue. This is when next we had our warm-up for all of our different quotes of wisdom. We heard from Mark Twain and Helen Keller and Gandhi, Ben Franklin, Jake, Call It 1.0, who came up with that, I don't know, Charles Kingsley, R.D. Carmichael, and then of course we played with, to learn math, you have to do now. So then our next statement was when we tried to figure out, what about if the converse and inverse are true and all 4 sentences are true, and we came up with this new notation, the biconditional, the double-headed arrow, where we realize you can say things forwards and backwards and have it be true, and that's where we learned our if and only if. And we realized that it was our definitions and our postulates that made this happen. Then we moved into our compound statements with our conjunction and our disjunction, recognizing that Venn diagrams had that overlapping part of where all things were true. We joked and laughed about Batman and the bathrooms and some testing situations. We practiced for the quiz, did some more homework, some more truth tables in practice. We did an activity on inductive versus deductive reasoning, which was our next conversation. And our deductive reasoning is where we went ahead and said, enough with all of this questioning, the anxiety and stress of wondering, is there a counterexample that's going to disprove me, is too much. So then Euclid gives us two rules of logic. Now notice we're still talking about if-then statements. We're still saying if and then, but now I don't have to worry about a counterexample. The law of detachment guarantees me that if somebody says if P then Q and P happens, I can count on Q happening too. I don't have to worry about whether there's a rule out there or some kind of counterexample. My law of syllogism allows me to link related statements together if I share a hypothesis and a conclusion of statements. We just did our truth tables as more practice. We started talking about using those laws of logic to help us solve algebraic equations and justify. So we reviewed our properties of algebra, our properties of equality, adding, subtracting the same thing to each side, multiplying or dividing each side equation by the same value. We talked about using the distributive property, which is not a property of equality, but is more of our properties of real numbers, like our commutative, our associative, our identity, our inverse. And then, of course, following the order of operations and simplifying. Our reflexive, symmetric, and transitive property of equalities might not have been covered in algebra, but we sure covered them in geometry when we compared using those big ideas with values, numerical, or things that are congruent. So at this point, we jumped into talking about using those things to solve algebraic equations. We talked about combining some geometry in there when we were using about angle measures, and then segment lengths, and talking about this. Our next page of notes had you doing, some of this for homework. Now this is what I'd like you to tell me. Are you filled out? Do you know this? Do you want to talk about this? Any questions on this page? I think we went through and talked about all these before the quiz. For homework, I asked you to complete the back of the notes 2-4, and we'll talk about that in a little bit. And then read through and look at deductive reasoning and proving angles are congruent. And then, of course, you have the back of that sheet to look at. Your homework looked like this, true? That's where I'd like to start today. So, go ahead and take this page out. And we'll start here together, talking about our Unit to proof practice, starting with solving an equation. Is it an algebra problem or a geometry problem? What defends the math I just did? Call it out. Call it out. Yeah. The distributive property. Distributive property. If you don't know the abbreviations, God bless you, write it out. Because some people put DPOE. Is there a distributive property of equality? No, because you're not doing it to both sides of an equation. So the distributive property is just where I take this -3, that's a coefficient to that expression, and I share him out to both the x and the -7.
So if there's a property and you put it in the justifications, you only add the of equality if you do it to both sides.
True statement. All right, now I'm going to clean this up a little bit. I know that this is 9x's. Sound okay? I didn't do it to both sides. What did I do? Yeah, I just cleaned it up a little bit. I put my x's with my x's. Now, some of your quizzes are graded like a big mess because you ended up, instead of combining my terms, adding and subtracting things individually. Your math was right, even though the order wasn't. So we'll have to go back and make sure that you got the points you deserve. All right. What did I do? I subtracted the same thing from each side. I subtracted 9x's here. I subtracted 9x's here. When I take the same thing away from each side, that is a property of equality. I divided the same thing by each side. Sound okay? Good?
Could you also add 33 each side instead?
Yeah, so if you're a person who prefers to kind of dance around your negatives, and that's kind of me sometimes, I gotta be honest with you. I always have this thing where I prefer to have my x values positive. So if I added 33x each side, I then have to subtract 21, right? So however it works out for you, this letter here is whatever you're doing. Are you adding or subtracting? So if you added the same thing to both sides, it would be addition property of equality. Does that make sense? All right. When we're talking about this one, we're mixing in geometry to get you into using each of these properties. In the diagram, B is the midpoint of AC. Let's stop for a minute and talk about what that looks like. B is the midpoint of AC. By definition, that means that the distance from A to B is the same as the distance from B to C because B is the midpoint and a midpoint creates two congruent segments. That's the geometry that needs to fly through your brain as soon as you read B is the midpoint of AC. All right, C is the midpoint of BD. Oh snap, this is fun. C is the midpoint of BD. So that means that these two segments are going to be congruent. Ah, you know what that's going to tell me? All three are going to have to be the same. Does that make sense to you? Logically? All right. So as soon as we jump in, the greatest thing about geometry is you're gonna get the first answer right. Hey, how do I know all this stuff? They gave it to me. Give it. How do I know that AB and BC, those two segments are congruent? Definition of what? Yeah. They told me it was a midpoint, so I'm going to use it. And here's it kind of like monkey see, monkey do. So because I did AB and BC are congruent, I know that then segment BC and segment CD are congruent by the definition of midpoint, because the same thing that they're showing me through my green example, I'm going to follow with my red. All right. Now it's telling me the distance from A to B is the same as the distance from B to C. And what this line is doing is it's connecting up to that idea. Two segments are congruent. I got it. That means they have the same distance. How do you know that? How do you know that? Who tells us that's true? The definition of congruence. How do you know that that's true? It's true because that's what it means to be congruent. If two segments are congruent, that means that they have the same distances. Are you already seeing the monkey see, monkey do? I'm going to do the same thing with BC and CD, and I'm going to go ahead and say, hey, that's the definition of congruence again. Here's a really cool part. If I have AB is the same as BC, and I have BC is the same as CD, do you see the link? Do you see how the conclusion of one becomes the hypothesis of the other? Go ahead. It is the transitive. Close. Transitive. That is the transitive property of equality. Here's a crazy story. I could have used the transitive property of congruence 3 lines ago. Do you see the difference between congruence and equality? I could have finished this a whole lot earlier. All right, what is it that I'm trying to prove? AB is congruent to CD. Now segment AB is congruent to CD. That is again going to be my definition of congruence, because this is where I go from numerical values to things. If you are aware of the transitive property of congruence, you could have done that 3 lines ago. Make sense? All right. When we're looking at MN and PQ, if I know that MN and PQ are the same, how am I going to prove that the distance from M to P is the same as the distance from N to Q? Think about that. We'll talk about that when you come back. It's real quick and easy. Christian, what's our given? Yeah, so I know that the distance from N to M is equal to the distance from P to Q. And the reason I know that is because they gave it to me. So the nicest thing about the proofs is you always get a point for that. That's something. All right? Now here's something that that might not occur to you. Go ahead.
So you said it's a point for the gift.
Yes.
Does that mean like on the test it's a point for every additional step you add? Or
No.
is it like every additional step that's correct?
So what we end up doing is instead of grading the proofs, because some people take 6 statements to prove it, some people take 4 statements to prove it. So when we talk about point value, we give you a point for your given, we give you a point or 2 for getting to where you need to go, and then another point at the end for having arrived. Do you know what I mean? So our grading of the proofs is a little looser than that. But that, at least you get a point for stating your given. Yes, that's true, if it's not already stated for you. All right. So let's talk about what I know to be true. Come on. I'm trying to prove that those two things added together are going to be equal to each other. So let's just talk about the blue statement for now. Let's just talk about Q to N. How do I get the distance from Q to N? Okay, so the distance from Q to N is equal to? The distance from Q to P plus the distance from P to N. And how do I know that I'm allowed to say that? Everybody say it out loud. The segment addition postulate. Okay? So while we're doing this, do you want to do the one for green? So we're doing them in tandem? We're doing them together? Who can give me the green statement? What do you think? Go ahead, Olivia.
NP is equal to MN.
So the distance from M to P is equal to?
The distance between MN plus.
The distance from M to N.
Plus the distance between, distance from N to P.
From N to P. Okay. I like it. Our goal is to show that these two things are the same. So we're given that MN and PQ are the same value. And we're given, anybody want to do any substituting? Anybody want to take a look at this? Given, and have some fun with that? Go ahead, Maggie, what's on your mind?
So I guess you're looking at the equations and you could substitute, one of, so like for the, NP equals MN plus NP, you could substitute PQ in there.
Yeah, and you get a choice. So do you want to put MN in for PQ, or do you want to put PQ in for MN? Which one you want to do? MN in for PQ. So that means that the distance from Q to N is equal to MN plus PN, right? And I know that that's true because of my substitution property of equality. Because these two things are equal, instead of writing PQ or QP, I was able to write MN. Now, if I wanted to be super duper picky, I can maybe talk about how the fact that the distance from P to Q is equal to the distance of Q to P, and I know that's my reflexive property, because I am spinning the numbers around a little bit. We're going to ease back and not be so fussy, but if you're worried about that, you can add that in. If you're confused about the PQ and QP. Do you see what I see? It's there. Who sees it? What do you see? And it's right. What? Doesn't that say the same exact thing? MN plus NP So can I say that can I say here that the distance from Q to N is equal to the distance from M to P? What lets me say that? So you've got two answers, and I want to show you the difference between them. It is the substitution property of equality. The substitution property equality can only happen with numerical values. So because this represents distance, I can put MP instead of MN plus PN, because these two are equal, so I can put that in and write that with no problem. If somebody was hung up on it being a transitive situation, you might need to go ahead and switch this around. MN plus PN is equal to QN, and that's our symmetric property of equality. And then what you have here is this conclusion becomes this hypothesis, and then I could say the transitive property of equality by putting in QN and MP congruent to each other. If you felt like doing transitive, that answer would be fine. Okay, when we get together next, we are going to continue talking about, wow, what happened here? We're going to continue talking about notes 2-5. We're not going to worry about that too much now, because we're going to do the back of those notes next week when we start talking about more of our angle proofs. Your homework had a back to it that also involved angles, but we're going to hold on to that and save that for when we talk about angles next week. The angle theorems and the angle proofs are not on the test next class. Sound okay? So we're going to talk about all that stuff next week. Sound okay? All right. So instead, what we're going to do,